This is Duke University.
You are all genetic engineers. And I know that to a room full of conservationists, that may sound like a dirty word, but it's true. Because every time you take action as a member of 7 billion human beings on the planet, you shape the environment of the other organisms we share the planet with. If you're like me and you're concerned about the idea of interfering in the future of an organism, ecologically or genetically, you are probably wondering, what could we possibly do about it if it's a matter of 7 billion people acting together with such tremendous influence? Well, that's what I'm here to talk to you about. I'm interested in the idea of assessing genetic conservation problems and attacking them at the genetic level. So here's an example of what I'm talking about. In a case like fish, we interact with an organism directly. When we come to a population of something like fish, we start exploiting it when it has something like what you see behind me. You've got big reproductive individuals, you've got a bunch of larvae kicking around, and you've got some intermediate individuals, of course. We first go for the big guys. They're the most resource efficient, they're what we want, they're the delicious fish. After a time, our pressure increases and we run out of the larger individuals. And this is usually the point at which we start to regulate. We say, okay, we're definitely going to keep eating fish. We're really hungry, we love fish, but we want to have them in the future. So we set some kind of limit. We say, all right, no one catch a fish bigger than these intermediate sizes, and no one catch a fish smaller than that. And we have this idea that by doing so, we're going to ensure that this resource remains sustainable well into the future. We think, okay, these fish have reproduced. It means that their offspring will grow up, and then we can catch them. But we keep up this pressure. Our population grows. People love fish. And eventually, we start to see something like this, where even at that limit, we're so good at catching all the individuals we say we can, that we create this weird environment where there's sort of a punishment for growing to the large size that this organism has evolved to grow to in order to reproduce. Under a selective regime like this, if one of these little guys that is free from our selective pressure develops a mutation that lets him reproduce, spread his genes in a way that is escaping human selection, all of a sudden, he's the new future of the species because he's not subject to all this pressure we're putting on through fishing, and his offspring will dominate the population. This might be a way for something that looks like a tuna to end up looking like something like a sardine because our pressure is so great and outweighs other ecological pressures. Now, this is an Atlantic bluefin tuna. It's a little bit taller than me, 6 to 7 feet long. This is the size at which we catch them now. Depending on who you ask and how optimistic you want to be, there's between 3% of these left and 40%, definitely a lot less than when we started measuring these things in 1975. However, what we still have a lot of is these, which are Atlantic bluefin tuna larvae. Because a reproductive individual produces so many of them, the proportion of the population of anything that might be called a tuna out in the Atlantic Ocean is now much greater composed of these little things, and lots of them die. But you're looking at the selective regime I just described to you theoretically. It's already been imposed. That's what we're doing. So if you're like me, you're just waiting for that mutation to come along. You're waiting to see this species shift its phenotype radically and respond to the single dominant pressure that it now experiences, which is fishing from humans. It's not only about changing phenotype either. We actually change the way that genes interact. We change the way evolution works. So in a population that's responding to what we might consider natural pressures, things that don't involve humans, so a few genes are relevant to various pressures in their environment. They vary at intermediate frequencies. Some individuals have them, some don't. They're usually not super rare. Usually, one mutation will convey a slight degree of advantage. Say, you've got a little mutation, you do a little better at high temperatures. Over time, you can accumulate a lot of these mutations. This would be a polygene, where a lot of low-frequency or low to intermediate frequency genes are accumulated in a way that lets you have a selective advantage. But under a human selective regime, the type of change we impose is so great and so rapid that it's not about having a slight change in an intermediate frequency gene. It's about having the gene that lets you survive arsenic poisoning. And that means, again, that we're not just changing the way things look. We're changing the way genes interact. This means that if you're the individual in this population who happens to have the low-frequency random mutation that lets you survive whatever humans have imposed on you, you'll be able to essentially override the entire ecological legacy of your species, since our selection is so great. And your gene will spread very rapidly, changing the appearance of your species, but also changing the way that the process of evolution usually occurs, that the processes of population genetics usually occur in the wild. These changes will persist even if we were to eliminate the pressures we impose today, even if we had eliminated them 10 or 20 years ago. So you're probably concerned because you know that we're not going to eliminate these pressures anytime soon. The population will keep growing, the Earth will keep warming, we'll keep using more resources, and all of these pressures will almost certainly increase. So what could we possibly do about it? This is an interesting case. There is a disease called citrus greening, or green blight. It is a viral disease of oranges that's spread by insects. It is so bad that when it shows up in an orange grove, the farmer who owns those trees will burn his entire crop to the ground just to give other farmers a chance to bring something to market that year. There is one way, once you're infected, to have a crop, which is to spray 3 to 4 times the volume of insecticide on your young trees, which kills off the insect vector for the virus and lets you bring the trees to market. You may have seen this newspaper article sometime over the summer in the New York Times. A CEO of an orange company said, well, we know we can use this method with pesticides, but that's terrible. It's a higher cost to us, it's a higher cost to the consumer, and it's a higher cost to the environment because we keep enforcing this very unusual selective environment by dumping and dumping pesticides. So he contracted some professors to come up with a GMO, something that would resist citrus blight and not require pesticide to do it. And they made an orange tree that contained a gene from spinach. That tree survived well, produced oranges, everything worked great. Then they went for FDA approval. Now, when you go for FDA approval, there is a public comment period. And when they submitted their wonderful new orange tree for public comment, they got the response that you always get when you bring a new GMO to public comment, which is universal and unmitigated horror. Because we have this idea that there's a line between nature and the laboratory. And it's one that people think, don't usually cross. What I'm trying to convince you of is that if there's a line at all, it's been crossed. Our influence, essentially accidental influence, is so great on the genetics of other organisms that we shouldn't even be thinking about whether or not we're involved in genetic engineering. We're doing it whether we want to or not. The question is whether we're doing it purposely and in a productive way. Now, I think that technology like this will ultimately be a pretty easy sell. I think conventional methods will get harder and harder to apply. I think that people will start to understand the benefits of technology like this, and will start to better understand the safety and what risks do exist. I think much of this will come to pass. But what about a case like extinction? So when an organism goes extinct, it takes with it hundreds of unique genes and thousands of unique genetic interaction patterns that will never be seen again. I think that if we had the opportunity to take one gene from a different species, insert it into an endangered species that's about to go extinct, and by doing so, allow that endangered species to resist the human presence in its environment maybe even to continue thriving. If we could do that using the technology at our command, I think we should do it. I think that in a world where we're causing extinctions at up to 1,000 times the background rate, we may be forced to do it. I think that eventually conventional conservation methods will start to fail more and more often in the face of the pressures we impose. So I want us to be ready. I want us to be ready with the science. I want us to be ready with the money. I want us to be ready with the moral discussions that you need to have about the implications for using science in this way. But I want us to start talking now, which is why I'm here today. I want you to understand what's going on, understand what's at stake, and understand your role as a genetic engineer in the environment, whether you like it or not. Thank you.